So this is the problem from IIT Advanced which we are going to discuss today. In the last lecture, we solved a very interesting problem on mathematics. Today we are back in physics, in the subject of physics. This is the problem statement, as you can see, though I am still going to read it out. A nuclear reactor starts producing a radioactive nuclide X from t equal to 0 at a constant rate of alpha per second. Each decay of X produces energy E naught, which is utilized to heat a liquid of mass M and specific heat S. Assuming no heat loss from the liquid and taking lambda as the decay constant of X, the rate of increase in the temperature of the liquid is. Now there are four options, as you can see. It was set in the IIT Advanced 2026, and let me remind you guys, it's a question with a single correct option. So now we are going to start the solution. The most important conceptual catch, again I would repeat, again I would reiterate, whatever the buzz around us says, it's not a tough problem. Most of the problem in the IIT Advanced examination, in the examinations conducted by the universities like the Jadavpur or the Jawaharlal Nehru University, are not tough. They just test the basic concept and skills that you guys acquire. So the main conceptual catch in solving this problem is, at first inside the nuclear reactor, the radioactive nuclide will be produced, and once the radioactive nuclide is produced, only after that, that radioactive nuclide will undergo decay to heat up the liquid, which is used as a coolant. Coolant is a very big issue in any nuclear reactor. This problem revolves only around heating up a liquid used as a coolant in a nuclear reactor. So here, if capital N denotes the number of the active nuclei at time t, then the rate of decay of the number of radioactive nuclei with respect to time will not be formulated as, please listen to this part again, will not be formulated as these will not be the equation to use. These will not be the equation to use. Why? On very few occasions, an instructor, a professor begins the lecture by stating what is not to be used. Mostly their duty is to say what is to be used. But this is the conceptual catch. If you start using this equation, you will never get to any correct option. This is the normal statistical law of radioactive decay, the textbook statistical law of radioactive decay that we learn. But still this is not to be used. Rather, it should be formulated as and if you can get this part right, you basically will be able to solve the problem. Because only after the radioactive nuclide is produced, then it can undergo the decay process and it can heat up the liquid which is used as a coolant. You need to understand this concept. Now suppose let the decay start at t equal to 0, and let, after the elapse of any finite time t, the number of radioactive nuclei be capital N. So this will be our equation 1. We will now separate the variable from these to write this equation as now we have to integrate within proper limit. What will be that proper limit? This will be the proper limit. And I think that it is not very tough to understand why we are using such limits. because I just said at any time t, capital N denotes the number of radioactive nuclei. Now we will make a substitution, we will make use of a substitution in this expression, in this equation. What is the substitution that I am going to use? Suppose so as soon as I make this substitution, you guys can see this is definite integration. So I need to make the substitution table which will change, which will give us the limit of the new variable introduced. What will be that? This is quite easy, absolutely textbook integration. N was the old variable, Z is the new variable. When N is equal to 0, make use of this relation, then Z will be equal to alpha. And when N is equal to M, then the way we have introduced the variable, it is not tough to understand that Z itself will be equal to Z. So, on the basis of this substitution, it's very easy to get to that step. What have we done though? We have basically differentiated both sides of this equation with respect to Z. And then switching over the variable is easy. dn will be equal to minus dz by lambda. Now with these modifications, the integral reduces to because on the right hand side there is no basic modification, integral of dt will be equal to t. And since it is definite integration under consideration, we avoid the use of constant of integration and its evaluation afterwards. Now there's time to change the page. I think so far it has been clear to all of you. So, if we put the limit in the last equation of the last page, we get to this step very easily. These are very easy, straightforward procedures, though I decide to show each of the steps so that anyone watching the video does not get confused about the steps. How did this come? How did this happen? Etc. etc. These queries. So we now reintroduce our old variable n. So in place of z, we are going to write where we have taken alpha in common when we are transposing the terms. So from these very easily this is an important equation. So far we haven't numbered any equation. Let it be equation number 1. Now, the rate of decay of the nuclide, or the so-called textbook activity at time t, is A equal to lambda into n. Then when we do that, we don't have this lambda bothering us at the denominator of this fraction. So we get this will be our equation number 2. Now, since each decay produces energy E naught, it was stated in the question, a condition of the problem, I repeat, each decay produces energy E naught, then the rate of energy production is dE dt, absolutely bare and basic calculus that we need. dE dt itself is equal to A E naught, understandably. This important equation will serve as equation number 3. Now, according to the problem, the liquid gets heated at this rate. This is the energy that is supplied to the coolant, and this is the rate at which it gets heated. So, very basic law of calorimetry, class 11 NCERT physics book will do for this formula. That's why I say it's not a tough question. M was the mass of the coolant, S was its specific heat supplied in the problem, the rate at which it is heated up. This should be equal to this guy. Right? Now we have another small differential equation to solve, where d of small dt of capital T is the rate of heating, and this will serve as equation number 4. So though we have a differential equation to solve, we don't require to solve it. That's how easy the problem is. What do we need to find out? The rate at which the liquid is getting heated. So we need to find this guy, which I have kept under bracket. Please see. So we only need to find these. This is the answer to your problem. You must have seen the option. This is equation number 5. Which option is it? I think by now those who have watched the video have got the option. Yes, option number A is the right option, is the correct option. So this is the problem, which in my view is absolutely simple. If you understand the basic process, a radioactive nuclide is produced. That radioactive nuclide is going to heat up the liquid used as a coolant in nuclear reactor. The coolant gets heated up at this rate. The idealized condition is used, no heat loss is considered. Normally that does not happen though. When you work as an engineer in a nuclear reactor, you will realize those subtleties, you will come to know about those subtleties. But here we are considering idealized condition, no heat loss is occurring. So very simply we are equating this guy to this guy, and then we need to find ddt of small t of capital T, which is option A. So that's how easy the problem was.